Exchanging energy between system and surroundings. So remember, the system can vary. It's whatever you define it as, and the surroundings would be everything around it. So we can have an exchange of heat energy. Heat is the mass times the specific heat times the change in temperature. We can also have an exchange of work. We talked about pressure volume work. So work is negative pressure times the change in volume. So here the system can exchange heat with the surroundings. The surroundings could do work on the system or vice versa. And those are the two different things that can go on there. The change in internal energy for a system is equal to Q plus W. And so we can find delta E by measuring Q and W. It's much easier to do if we make one of those 0, right? So if we make 0 W, then delta E is equal to Q, and Q is much easier to measure. Well, how can we make W be 0 if we're doing pressure volume work? What's pressure volume work? It equals negative pressure times the change in volume. If we don't allow the volume to change, then that's going to be 0, right? And the work done will be 0. So that's what we do. We use a constant volume, and then the work is 0. So at constant volume, the change in the change in energy for the reaction is equal to Q. That's the heat at constant volume. So that's got a little subscript V down there. It isn't practical to observe temperature changes of individual chemicals, right? Because we did an experiment like this on Tuesday. We did calorimetry, and you mix things together in the little styrofoam cup calorimeter. And how do you measure the temperature of one and not the other, right? You can't, because they mix together. So what we do is we measure the temperature change of the surroundings. This is not the type of calorimeter that we used. A bomb calorimeter uses insulated and controlled surroundings. Then what happens is Q for the system must be equal and opposite to Q for the surroundings. Another way to think of that, what color am I in? Oh, orange. Orange is fine. Q for the system plus Q for the surroundings has to equal what? The heat lost by the surroundings, gained by the system, has to be 0. They have to add up to 0. And so that's where we get this from. The heat gained or lost by the system is equal but opposite in sign to the heat lost or gained by the surroundings. And so for this technique of calorimetry, we call that Q-cal, so the heat absorbed by the calorimeter. Calorimetry, calorie refers to heat. Metry is measuring. It's a technique used to measure the heat of a reaction. So we observe a change in the temperature of the surroundings, and from that we can figure out the heat that was given off by the reaction. This is a bomb calorimeter. This is much fancier and more expensive than what we used, which were little tiny styrofoam cups. So this is an illustration of a bomb calorimeter. We've got water in here, and inside we have this little, it's called a bomb. It's not going to explode though. A little bomb, and it's tightly sealed, and the pressure, I don't want to talk about the pressure. Here's the sample in here, and there's oxygen, and so we can measure, for instance, the heat given off when a peanut burns. You've got oxygen in there, you've got ignition wires in there, and so this is really useful for combustion reactions. They're going to give off a lot of heat. Where's the heat going to go? Well, the heat's going to go through the bomb calorimeter, the bomb inside here, and it's going to go into the water, and the water will increase in temperature. We can measure the increase in temperature, and then we can calculate how much energy was given off. So the calorimeter constant is really the heat capacity of the calorimeter, the amount of heat absorbed by the calorimeter for each degree rise in temperature. And that's something that needs to be calculated experimentally. And you did that yesterday on your little cheapy calorimeters by just mixing hot and cold water. And then we're going to calculate today. Yeah. So let's look at an example. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. So a picture is going to be helpful here. So we've got our large calorimeter, and then on the inside we've got the little bomb. And in the bomb we've got 1.550 grams of hexane, C6H14. And it's going to undergo a combustion reaction. Could we write a chemical equation for the combustion of hexane? Say yes. Yes, we could. And oh, let's do it because it would be so much fun to review that. What do you need to burn something? Oxygen. So there's the hexane, and it's going to react with oxygen. And what will the products be? Carbon dioxide and water. You do remember some of this. And then we have to balance the equation. So I'm looking at 6 carbons on the left. I'm going to make 6 carbons on the right. 14 oxygens on the left. So if I put a 7 here, I'm going to get 14 hydrogens on the left. And then I'm going to end up with an odd-even problem because I've got 7 oxygens and 12 oxygens. And that's going to be an odd number. So what I'm going to do is I'm going to double things. I'm going to make this a 12, and I'm going to make this a 14, and I'm going to double the 1 there. So now I've got 24 oxygens and 14 oxygens, and I believe that will give me 38. And if I divide 38 by 2, I think I should get 17. No, 19. Yeah, 19. The 7 didn't sound right, but I didn't know why. 19. So there's a balanced chemical equation. We don't need this anymore. What else are they telling us? The temperature rises from this temperature to that temperature. So we probably need the change in temperature. We could figure that out. Maybe blue. So delta T, it's always the final minus the initial, from 25 to 38. So 38 is the final, 38.13 minus 25.87. Always forget my calculator. $38.13 minus 25.87. 12.26. Degrees Celsius. It's the change in temperature. It says the heat capacity for the calorimeter. What's the letter that we use for heat capacity? C. So I'll call that C calorimeter equals 5.73 kilojoules per degree Celsius. What's unusual about that specific heat? Well, it's got kilojoules. it doesn't have grams in the denominator, right? The other ones were grams, joules per gram degree Celsius, or calories per gram degree Celsius. This doesn't have grams in the bottom. That's because this calorimeter constant applies to this specific calorimeter. Another way to think of it is, it's like you had the mass of the calorimeter times the specific heat capacity, and you got this. So if we just think about units, how much energy did it take to heat up the calorimeter like happened? If we just look at this number with kilojoules per degree Celsius and this number, what could we do to get kilojoules out of that? Just multiply them, right? So Q for the calorimeter is going to equal C for the calorimeter times the change in temperature of the calorimeter. So that's 5.73, can't read my own writing, kilojoules per degree Celsius times 12.26 degrees Celsius. The degrees Celsius cancel out, and we get 70.2498 kilojoules. How many significant figures should that number have? 3. So I'm going to underline the third digit there. What did we just calculate? It was heat, right? Was that the heat that the calorimeter absorbed, right? Where did that heat come from? The combustion reaction inside. So the combustion reaction gave off the same amount of kilojoules, it's just that the sign is the opposite. The calorimeter absorbed heat, that was endothermic. It was a positive for the calorimeter. The reaction gave off heat, it was exothermic, and so it's negative. So what we saw in the previous slide is that Q for the calorimeter is equal to minus Q for the reaction. So that makes Q for the reaction equal to minus 70.2498 kilojoules. Does that make sense? What was given off by the reaction was absorbed by the calorimeter. It's very hard to measure what was given off by a combustion reaction, but we can measure the effects of it because the heat that was given off caused the temperature to rise, and that's easy to measure. What are they asking us to find, though? We found Q. They're looking for delta E for the reaction. And they want kilojoules per mole of hexane. This amount of heat in kilojoules is given off for how much hexane? For this much, right? If we use 2 grams of hexane, would Q be the same or different? It'd be different, wouldn't it? You burn more gas, it's going to give off more heat. So we need to relate this amount of energy to this amount of hexane. We have our equation here, and we're going to find out how much energy was given off. So we need kilojoules per mole. Well, could we figure out how many moles of hexane? We could. Let's get rid of the word example. So we need the molar mass of hexane. 6 times 12.01 plus 14 times 1.008 86.172. That's grams per mole of hexane. So then we can take our 1.550 grams times 1 mole per 86.172 grams. And I'm going to get 0.017987281. I just wrote everything down. Moles. Which of those digits has uncertainty in it? The 8. This number has 4. As I used rounded molar masses here, this one also had 4. And so the 8. And I'm not going to round it off, but I'm just going to underline it because it makes it easier later. So if we want kilojoules per mole, all we have to do is take the kilojoules and divide by the number of moles. I'm not sure where I'm going to do that, though. I'll just make some more room right there. So 70.2498. I really need to get some more styli, because this writing with my finger thing is getting old. So, oh, bless you, and it's even pink. Oh, awesome, thank you. That's so much better. Okay, so I just underlined my sig figs so I wouldn't get confused. I've got, I still have that number in my calculator. I'm just going to reciprocate it, upside down it, I don't know, and multiply by negative 70.2498. And I come up with minus 3905.5. Blah, blah, blah. So that's going to round to minus 3906. Oh, that's not what I wanted. Come on. Need a little more space. Kilojoules per mole is our answer, hiding in there. Now here's a question. If I wanted to write delta E reaction for this equation, usually when we see these, they are written just in joules or kilojoules, and they don't say per mole. When it's written as part of the equation, it's written for the molar amounts in the equation. So I can either take this number and double it to write it in here, or I could divide all my coefficients by 2 so that I end up with 1 mole of this. The question doesn't specifically ask us to do that, but it could come up later. Does anybody have any questions?
So that was an exothermic reaction?
Yes, it was an exothermic reaction of the hexane burning.
So if it was indo, it would be positive?
Yes. The reaction feels the same way about its energy as you feel about your money. Right? When it comes in, that's a positive thing. When it goes out, it's negative. Works for me.